We're back here in E641 learning about optimization of non-quadratic functions. So you might ask, well, why would our functions be non-quadratic? Well, it's because we're going to have non-Gaussian priors. We might also have non-quadratic functions if we had like nonlinear forward models, but let's not worry about that right now. But if you have a non-quadratic prior, the thing that you get is, okay, if you have a non-Gaussian prior, then it's not going to be quadratic. Because remember, the log of a Gaussian distribution is a quadratic form, right? Because it's always an exponential of something like x transpose r inverse x, right? So it's always a quadratic form. So when you take the log of a Gaussian, of the density for a Gaussian distribution, you get a quadratic form. So when you do the map estimate, you have quadratic optimization, right? Because the log of that prior distribution is quadratic. But the problem, what's the problem with Gaussian distributions? Well, the problem is that they're not very good models for real images, because images, the statistics of real images is not Gaussian at all. So like, for instance, I give this example. If you take pixels next to each other and you histogram them, the distribution you get is not even a little bit Gaussian. Has anybody tried that, by the way? It's like a 15-minute experiment in MATLAB. Just take. You tried it?
Yeah, but I can bring it next class.
Oh yeah, bring it next class.
Yeah.
Okay. So you don't want Gaussian. So we've come up with this Markov random field model where we reparameterize the Gaussian in terms of squares of differences between pixels. You can always do that. And then we replace the square with some other function. Some function that doesn't grow as rapidly as the square, because as that function grows more rapidly, that's basically the negative log probability, right? Because in the Gaussian you have e to the minus 1/2, and then you have x transpose r inverse x. So there's a quadratic form, but you take the negative. So as you get further from the center of the distribution, the probability goes down, because the quadratic expression gets larger. The quadratic expression goes up, the probability goes down, okay? But it's e to the minus. So if that quadratic term gets too big too fast, then the probability of that thing gets really small. A Gaussian model doesn't accurately model the edges, because it says that the probability of an edge like that is really, really small. It's really not that small in real images. It doesn't occur all the time. So you have now a model which is a Markov random field where you take differences between pixels, but you don't allow it to grow as fast. So now it's not quadratic. Now, remember, we went through the different models. You can have a convex function of the difference of the pixels. You have a non-convex function. We're mostly going to talk about convex functions. So an example would be the difference between the pixels to the power p. If p is 2, that's quadratic, and then that's Gaussian. So quadratic goes with the Gaussian, okay? Non-Gaussian goes with non-quadratic. So you have p less than 1, say like p is 1, or p is 1.2, or 1.1, then that's not going to be quadratic, and now it's not Gaussian. But the good news is you can model real images better, because you can capture the edge behavior, okay? But the bad news is now you have to do the optimization. It's not quadratic optimization anymore, so how are you going to do it? Well, you can do things like coordinate descent, and you can do gradient descent, but now the line search is the tricky part, because the line search is now not a quadratic function. If you move along a line in a quadratic function, then the one-dimensional function you get is quadratic too. If I took any quadratic function in a high-dimensional space and take a slice through it, the slice I get also looks quadratic. But if it's a non-quadratic function, this function along that slice is not going to be quadratic. The line search isn't a quadratic function. The fact that when the line search is quadratic, it was a lot easier to solve it, because if I have a quadratic function, let me draw here. If I have a quadratic function, it looks like this, right? If I knew the first and second derivatives of this function, I can find the minimum I only need, for a quadratic function, the second derivative is constant, right? So if I know the first and second derivatives right here, I can find the update. The other way of looking at it, by the way, is if you take the derivative of this function, the derivative of a quadratic function derivative of a quadratic function is linear, right? So let's see, the derivative of this thing is going to start off negative and it's going to go positive. So it'll be like this. Okay? This is the derivative of that, right? So if I know the value of this function and its derivative, that's the same thing as knowing the first two derivatives of that function. So I can root this function. So finding the minimum here is equivalent to rooting this. And the root to this is easy enough to calculate. So this value here will be, say, f prime of x prime. So it's the first derivative. This is f of x, right? So that's the first derivative. Let me make this an alpha, because in the 1D case we're calling that alpha, okay? So that's f prime of alpha prime, right? And then the derivative, so the slope here, is f double prime of x prime, right? That's the derivative. The second derivative of this is the first derivative of this. Right? Because this is the derivative, this function is the derivative of that function. So if I want to find the point of intersection, when I drew this, it looks like it's always intersecting at 0, but it doesn't have to intersect at 0. It can intersect somewhere else, okay? So if I want to find this point, how do I find it? It's a simple geometry. I know that this value here is f prime, right? And I know that the slope is f double prime, right? So the point of intersection will be like, and this point here is alpha prime, right? So this point here is going to be, I take alpha prime, right? And then it's going to be like minus, okay, so it's going to be plus, I think, f prime of alpha prime over f double prime of alpha prime. Isn't that correct? Let's see. Yeah, because it's negative and the slope is positive. Oh, maybe it's minus. So if I go that far, or maybe it's, hold on, there's a constant 2 here. No, because this, let's just work it out. So this distance here, right, is going to be equal to the slope times the change, right? Oh, okay, so that distance is going to be minus f prime of alpha over alpha double prime of alpha prime, right? So this is simple geometry. This is the Newton update. That's a minus. Okay, this is the Newton update in the Newton-Raphson algorithm. That if you know the value of the function and you know its derivative, you just take a ruler and draw a line and find the point of intersection. And the point of intersection is given by this formula over here, which is alpha prime. For those on TV, I know you probably can't see this too well, but I'm just illustrating this graphically. All the formulas are in the notes. This is just to give you the flavor of what we're doing here, okay? So this all works out exactly if it's quadratic, but if it's not quadratic, then this is going to be approximate, right? So how do you find the minimum? So in the quadratic case, it's easy to root the function. It's easy to find the minimum of the quadratic, okay? In the non-quadratic problem, what are you supposed to do? Well, one possibility is that you use binary search, and you search this interval for the root, okay? You're doing that in the lab, correct? Everybody, have you actually done that yet in the lab? Or are you still working on that? Huh?
Second part of the...
Okay, so you haven't, so that, I don't know what's going on with this crazy thing in the box. Okay, so let me redraw this. So in the binary search, if you're doing the routing, you start here, all right, and then you find, this is A, and then you find a point B, okay, and you say, oh, well, the solution is somewhere between those. So you take, say, the half of that waypoint, and then you reevaluate the function, and you say, oh, now it's between, you make this A. And then you take the halfway point, and you make this B. And you keep narrowing it down until you find a point in the middle. And then the last thing you do is you take this point, and you draw a line and find the point of intersection, okay? Okay, but the problem is that requires that you evaluate the function a lot of times, because every time you evaluate the function, it's expensive to evaluate the function. Because remember, this function is really f, the big function, and then you get your current point, xk, plus alpha times dk. D is the direction of update, and alpha is, you're doing a line search along alpha. So every time you evaluate this function, you have to evaluate this whole function. It's expensive. It's computationally expensive. So you don't want to have to evaluate it so many times. You know, it's like, so how do you guess where the solution is with just a small number of samples? Right? So that's where this majorization technique comes in. In the majorization technique, I'll switch to the document camera because I know it's easier to see. Oh, I just turned it off. I did the wrong thing. Okay. Is it kind of, okay. Okay, in the majorization technique, you have a function which is, say, not quadratic. Okay? And you have, so finding the minimum, you know what the value of the point is, this is your current value, alpha. Okay? So now what you want to do is you want to try to figure out where the minimum is. And you can say, well, it's obvious, it's right there. Well, but you don't know that because you can't see the curve. Evaluating each point on this curve is very expensive. So all you know is that the current value of the function is equal to this, okay? So what you do is you say, maybe you also calculate the local derivative of that curve. So now what you do is you put a quadratic function, you have a quadratic function which upper bounds the curve and is tangent to it at the current point, then you can solve the minimum of the quadratic function and you're guaranteed to have reduced the actual function you're minimizing, okay? So, that's this picture right here. So, Q is the upper bound, is what I'm calling the substitute function for f. Now, in addition, you can take Q and you can add any function of x prime to it, and it doesn't really matter. You're minimizing with respect to x. So any constant you add to this, which is not a function of x, doesn't matter. So, yeah, you have a question?
Yeah, that's for the quadratic method. If the curve is intersecting the x-axis, then we can use the Newton-Raphson method in that case. If it's minimum marking, like.
Okay, so if the curve, okay, so you could use the Newton-Raphson method. Are you talking about on the function f? Can you use the Newton-Raphson method?
Yeah.
So now what will happen is that essentially the substitute function is a little bit like Newton-Raphson, okay? Because what you're doing is this. So let's say you have this function, right? And then you have its derivative. Its derivative is, say, something like this. Okay? Now the problem is, if you use Newton-Raphson, you calculate the first and second derivatives here. Then what will happen is that you will draw a straight line. It goes off the page. So, and now you'll go up here, and you draw a straight line. Okay? Newton-Raphson is not guaranteed to converge. Let me do that again. Okay, so let's say let's say I start here. I might go, well, actually, this is, okay, let's say I start there. I'm going to first go to here, okay? Then I'm going to go to here. Then I'm going to go to here. Here, right? And then I'll go to, I guess it works. And then I'll go, you can see it's not ending well, okay? So, Newton-Raphson is not guaranteed to converge. It can diverge. If you get into, because you're predicting where it's supposed to be, you could overshoot, okay? So, so the substitute function has an interpretation in derivative, but it's easiest to think about it as a minimization function. If you differentiate everything, then it becomes a rooting. So finding the local minimum of a function is equivalent to rooting its derivative. So, okay, but this is guaranteed, that every update is guaranteed to make the function smaller. So it has to converge. You have a monotone decreasing sequences of function values, which are bounded below. So therefore, it's got to converge to something, okay? Even if it's not a local minimum. In fact, it will converge to a local minimum as long as you put some reasonable conditions on how you select this stuff. Okay? So, but one of the questions, does everybody understand how the substitute function works? Okay. Now, but one of the problems with substitute functions, so then the next challenge, well, how do you pick a substitute function? So one possibility is this. You can say, okay, I'll pick it so that, and there's a various, so then becomes the optimization technique. Okay, this is the condition. The condition is that f is strictly less than this, okay? So this looks kind of like a complicated mess, but this is equation 7.17, but it's actually not so bad. Okay, so what you're saying here is that for all x, here I'm just subtracting off the value of x at x equals x prime. So that would make this function here 0 when you evaluate it at x. And then I add back the value at f prime. So now you're sure that at f prime, the right and the left functions will be equal. Okay? The second, okay, but at any other value of x, the right equation is an upper bound. So this thing here, this whole function here is the substitute function q of x semicolon x prime. Because it has the property that it's equal to f at x equals x prime, and it's a strict upper bound everywhere else. But in practice, it's easier to use this function q than the little function q. From the big function q, you can always generate the little function q, but the minimization of both these q's results in the same thing. They're just different by a constant. Because everything else here is a constant. Nothing here is a function of x. Is that clear? I know that must, I mean, if you don't know what I'm talking about, what I just said probably sounds like gibberish, okay? Because there's like a lot of words in that sentence, but the concept is a really simple one, okay? All I'm saying is that you can shift the function up and down, it doesn't matter. Okay, and then, so if you're doing minimization, this is the correct thing. If you're doing maximization, that's the correct thing. Okay, and then there's some other kind of relations here that so then, once you have a substitute function, this iterative minimization of that substitute function, so what you do is you minimize with respect to x, and then you update x, k, to be the new value of x, and you just repeat, okay? By the way, I mean, if you could solve the original function, if you could solve x hat equals the R min over x of f of x. If you could solve this, then that would be easy and be done. The problem is that f might be a complicated function and you don't know how to solve it. So instead you find this thing q of x, semicolon xk minus 1, and you minimize with respect to x, and that produces the next value of xk. And then you just repeat. Okay, and then this will converge to that. Now, or at least it'll converge to a local minimum of that. Now there's some other addition. Okay, so here there's some interesting facts. The gradient of f at the point x prime is got to be equal to the gradient of the q function at the point x prime. Well, that's only because if it's an upper bound, it has to be tangent. Right? There's no way you could have something that's not tangent and be an upper bound and be continuous. Because if it were not tangent, it would have to go below the line and then it would be an upper bound, right? So, and then there'd be 6-point properties and so forth. Oh, okay, this is important. If you have a substitute function or a surrogate function for a function for individual functions, so if f is composed of a sum of little f, of x of n, and you have a substitute for each function for each x of n, then the sum of the substitute functions is the substitute function of the sum. Okay, I'll say that again because it's sort of a little bit like Sally sells seashells by the seashore, okay? It's the substitute function of the sum is the sum of the substitute function. I think that's actually the correct statement I said there. Oh, it mostly just sounded good. Okay, so, all right, that's very useful because what we're going to do is we're going to find a substitute function for each one of these little potential functions, and we're going to substitute it in for all of them, so we'll have a substitute function for the whole thing. Oh, this is kind of an interesting thing. Composition of substitute functions. Actually, every once in a while you can prove something useful with this technique, but that, yeah. And, okay, so now, coming back to the original problem, this is the problem we need to minimize, equation 7.22. So, this part's quadratic, the likelihood is quadratic, log likelihood, but the problem is the log prior is not quadratic, right? So you have these row functions. So what you really need is you need a substitute function for the row function. If you have a substitute function for the row function, then you're good because you can substitute those substitute functions in for each of the row functions, and then you have a substitute function for the whole thing. You do that minimization and you repeat, okay? So how is it going to work? Okay, so then what ends up happening is that, so the upshot is, I need a substitute function for the individual row function, okay? Once I have that, I'm good to go for the whole thing. Now, I think the thing that's confusing here, well, first of all, you've got to read the notes, okay? Because I can talk about this, but if you don't read the notes, it'll just be, I mean, I may as well just be speaking like Martian, okay? Because, I wouldn't pick any language spoken on Earth because there would likely be somebody in the classroom who speaks it. So it must be Martian, okay? I'd be like speaking Martian if you don't read this. But you have to have it in your head first, and then it will make sense. But you see the prime, what's the difference between having the prime here and not having the prime? That's critical. The prime is the previous value. The unprimed case is the next value, okay? So, rho here, so we need this function rho of delta semicolon delta prime, right? Okay, now we know it's going to be a quadratic function of delta. Delta here is the difference between the pixels, and the delta prime is the old difference between the pixels, and the delta is the new difference between the pixels, okay? Because I'm using my previous configuration of the image, From that, I calculate the substitute function, and then I minimize the substitute function rather than the actual function. And I change the image, and I repeat, okay? So it's got to have this form, okay? It's got to have the form that it's a quadratic function. I mean, okay. So we have a function, okay? That's the function where that's going to be rho of delta, okay? And now we're going to be at some point, call this delta prime. So this is the delta axis, but we're one point on the axis is delta prime. So this is where we are, right? And now we're going to have a quadratic function. And it's going to be tangent at that point. So this function here, okay, is tangent at that point. So Q of delta, semicolon, delta prime, is going to have the form, I'll call it A0 plus, it's going to be A1 times so delta minus delta prime plus A2 over 2 times delta minus delta prime squared. So it's like a Taylor series expansion. Oh, let me zoom out. It's like a Taylor series expansion about this point. So now the question is how I pick these coefficients. Well, A0 will have to equal rho at delta prime. Now, but guess what? I said that, oh, shoot. Zoom out. Because I'm matching up the values of the function. That said, I don't care about this. I don't care about any constant I add to the function because I'm minimizing it. I only care about the argument that produces the minimum. I don't care about the value of the function as minimum. So while this is true, I don't have to worry about it. Okay, I can skip it. I'll put a little X here because I can skip it. It's true, but I can skip it. A1 has to be the first derivative. So A1 is going to have to be rho prime at delta prime. It's going to be the first derivative. And A2 is going to have to be the second derivative because the second derivative of this quadratic function is A2. I mean, if you differentiate this, right, the 2 cancels out the 1/2. This is just a Taylor series expansion. So it's going to be rho double prime at delta prime. Or, no, actually that's a lie, okay? It's going to have to be greater than or equal to rho delta prime. It doesn't have to be equal. I don't have to match the second derivative. I just have to be greater than it, right? Actually, in fact, well, that's a necessary condition, but in fact, it's not sufficient. Because what I really have to do is pick A2 to be large enough that I'm sure I upper bound it. In fact, what I'm really going to have to do is this. I'm going to have to pick A2. This A2 is the hard part, by the way. Okay, A1 is really simple. A1 I just set to be the derivative, okay? But A2 has to be greater than or equal to the maximum over delta, okay, of rho delta prime of delta. In other words, if A2 is larger than the second derivative of the function at any point along the curve, then I'm sure, I mean, you can prove that this has to be an upper bound. Right? It's like if you have a race car and one car is turning more sharply than the other everywhere along the road, then it's got to turn more sharply than the car. That's a really bad analogy, but hopefully it at least wakes you up a little bit. Okay?
Can you smooth the paper up?
Yeah.
What if we have to have the maximum dog max? Because dog max.
Not the argmax, just the max. You're talking about this term here, that the A2 has to be greater than the maximum of the second derivative of rho over delta.
Does that make sense? So you have to match the first derivative at your current point, and the second derivative has to be greater, okay, the second derivative has to be large enough that I'm sure that this function is bounding above
the other function. But one way to achieve that is for
the derivative to be greater than the derivative anywhere on the, if it's uniformly greater, if A2 is uniformly greater than the second derivative of rho everywhere, then you can easily show that you've achieved that goal. Yeah?
Now, when you put the max, it's sufficient, but it's not necessary.
It's sufficient, but it's not necessary. Right. In other words, it may be a smaller value of A2
Can achieve the same goal. Right, which was exactly my next point. You're like perfect. I think I must have planted you. I probably agreed to pay you something after class or something for that question, because it was precisely the correct question to ask. That, okay, this guarantees that it's a substitute function, but it might be a little bit conservative, right? So, now, if it's conservative, what happens? Well, maybe that's fine. So what? I can still guarantee conversion. Is that a problem?
Let me draw the picture again. So, let's say that's the true row. Okay? And now let's say this is our current point. And we pick a really large second derivative. It's got to be tangent.
So it's like this. So now the second derivative of the substitute function is really large. It's definitely upper bounds it and it's tangent. So it's a substitute function.
When I go to do the update, I'm going to just take a teensy-weensy little
Step, okay?
and then I'm going to do it again.
And I'll take another teensy-weensy little step, right? So what's the problem with this?
Slow conversion.
The convergence is going to be really slow. So really what we want, you can't actually prove that this is optimal, but, okay, at least, okay, intuitively, the thing that's optimal in the sense of giving us the biggest reduction in this cost function is we want the sort of tightest upper bound. What we really want is we don't want just any quadratic function. We want the quadratic function that's a tight upper bound, right? So the function kind of looks like this, okay, right? So this is our current point, delta prime. So it's got to be tangent there. So if I make the function tangent there and I grow the quadratic out, and I increase as I reduce the value of A2, right? So A0 equals rho of delta prime. So that's constant, but we really don't care about it. We actually skip this step, but we can include it conceptually so that the picture is correct. And then A1 is equal to rho prime of delta prime. Right? And then, so what will happen is now as the value of A2 gets smaller, right, then this thing is going to grow, right? And what's going to happen? When does it stop growing? When it touches. But once it touches, if you grow it any further than that, now it's not going to be an upper bound. So when is it going to touch? Where is it going to touch? Well, for this kind of a function that has the symmetry properties of what I'm drawing here, it's going to touch right here, right? So you're going to get a function that kind of looks like this. It's like you have a crevice, okay? You have a crevice and you take a ball bearing. Well, it's not exactly a ball bearing because it's parabolic, but let's pretend it's a ball bearing. You drop the ball bearing in, it's going to fall, boom, into the hole until it gets caught on both sides, okay? And on both sides, it'll be tangent where it touches. Got it. So so that's what's going to happen. So now you can sort of see, okay, so if rho is a symmetric function, and that's the point of symmetry, okay? So this is 0 because, remember, rho of delta equals rho of minus delta. It's a symmetric function, right? So this will be 0. So if this is delta prime, then this point here will be minus delta prime, right? And if that's the case, then, well, you can calculate the second derivative because you know that this thing here is the derivative 0 here, right? So what you know here is that, let's see, A2 is going to be is the second derivative, right? So A2 is the second derivative. So the second derivative is the rate of change of the first derivative, right? So here the first derivative is actually well, okay. Here the first derivative is 0, right? And there the first derivative is rho prime of delta prime. So A2 has to be rho prime of delta prime minus 0 over delta prime. Okay, I did that kind of quick, so let's do that again, okay? At this point, the derivative of the substitute function is 0. At this point, the derivative of the substitute function, at that point, the derivative is rho prime of delta prime, right? So the derivative the first derivative went from 0 to rho prime of delta prime over a distance of delta prime. So the second derivative must be rho prime of delta prime minus 0 over delta prime. So this is the formula, assuming I did it correctly, for the sort of most commonly used quadratic substitute function. See, and this is the picture here, and see the 7.7. It says, okay, and I call it the symmetric bound because it has this sort of symmetry condition. It doesn't always work for every function, okay? Like if the function's not convex, for instance, it definitely won't work. There's some conditions you need for the function, but for the functions we'll be using here, it generally works. So, see, A2 is this, and the beauty of it is that what's A1? Well, if you reparameterize a little bit, it looks like this. Okay, so you've got, okay, so now, so that's this is rho of delta, okay? This is delta prime. This is minus delta prime, okay? And then you have the quadratic function, right? So what's the equation of the quadratic function? So the quadratic function is rho of delta semicolon delta prime. So rho of delta semicolon delta prime. Well, first of all, we don't care about any constant value, so it's going to be equal to A0, but we can, without loss of generality, just set A0 to 0. Okay. Then what's the first derivative at 0? Because this is now 0. The first derivative of 0 is 0. So this is going to be plus 0. So this is good. So far, it's 0 plus 0. That's easy to keep track of. And then what's the second derivative? Well, the second derivative is going to be, now it's going to be delta squared, okay, times something over 2. And over here we put that's A2. And A2 is just going to be equal to what? It's going to be equal to rho prime of delta prime over delta prime. Did that like get a little bit confusing? Did you follow that? Okay, good.
My question is, Professor, if the row delta doesn't, will the row delta always touch the lower axis at 0? Will the minimum always touch the axis at 0?
Oh, for the row, for this function?
Yeah, for row delta.
Well, first of all, we don't care, because even if it doesn't, you don't care about any constant. But in general, the functions we take, we usually, without laws of generality, for these row functions at least, we make them 0 as 0. But if they're not, it doesn't matter anyway. Because that's just a constant. We don't care about any constant, because all we're doing is, the only purpose of these functions is to, when we minimize the function, we're just looking for the argument that minimizes them. So we don't care about any additive constant. Actually, that's like half this course, realizing, taking track of all the additive and multiplicative constants that we don't care about, okay?
So that makes like the computation like a hell of a lot easier.
Yeah, it's really simple, okay? So all you need to know for this substitute function is to know the derivative of the function at the current point. That's all you need to know, okay? So now what you can do is tabulate. Okay, so that if you were solving, okay, this is, I call this the Russian doll effect, which is that, you know how you have the Russian dolls and you have, like you put a doll inside of a doll inside of a doll, okay? And sometimes you can start getting busy, okay? When too many things start attaching to each other, okay? And you thought you were really clear about each of them, and all of a sudden you woke up and you can't remember. You were trying to stick a peanut butter and jelly sandwich inside of a computer or something. You're like, oh my God, I don't understand why I'm doing this anymore. Okay? So you have to go back and sort of unwind it and get it all clear in your head. Okay? So this is the original function we were solving. This is equation 7.22. Okay? You have this quadratic term, that's fine, we know how to handle that. And then you have this non-quadratic term. We're going to find a substitute function for each of these individual rows. The choice of substitute function will depend upon the current value of x, which will mean that it's going to depend upon the difference between xf and xr at each pixel pair. So for each pair of pixels, you're going to use the difference, the value of the difference of the current value of the difference in that pair of pixels to pick your parameters of the quadratic. Now, if you do that, then what will happen is that, and you use this symmetric function, this is the result you'll get. So the primes are the previous values of the x's, and the unprimed are the current values of the x's. So this function, 7.29, is only a quadratic function of x. So we took a non-quadratic function of x, and we made it a quadratic function of x. See, 7.22 is a non-quadratic function of x, but 7.29 is a quadratic function of x. So that's good, but now the weights on that quadratic are a function of the previous pixel value. So sort of the way to think about this is that you look at each pixel pair, and it's sort of an adaptive method. Based upon the current difference in the pixels, you weight that click more or less, and then you solve a sequence of a series of quadratic problems instead of trying to do the non-quadratic problem. The advantage of this is you avoid the line search. You don't avoid, you don't avoid the line search, but what happens is that when you do the line search, it's now, solving the line search on here is quadratic, so the line search is really simple to do. The whole reason you wanted to turn it into a quadratic function is because line search is much easier for a quadratic function. Otherwise, the computation associated with the line search will dominate the computation of doing the optimization. Yet, this is a pretty tight bound. See, it's a pretty tight bound, so when I minimize with respect to this quadratic upper bound, I get something pretty close to the minimum of the true function. So it converges pretty rapidly.
Now, the particular, yeah.
Why would you get something close and not exact? Because don't you have the minimum of the quadratic and the non-quadratic, or the
Yeah, because in this particular case, the minimum of these two functions is the same. But now what's going to happen is this. There's something I'm sort of slipping by you. You know, I'm like a little bit, you know, I'm kind of evil, let's say. Because what I do is I get you to agree to things, and then you go, oh, yeah, and then I kind of lead you down the right path. So the thing is, remember I got you to agree to the idea that if we have a substitute function for each individual row, and we add them all together, we get a substitute function for the whole thing. Okay? So this is the figure 7.7 is a substitute function for just one of the rows. Now when you add them all together, you get a substitute function for the whole thing. But this whole thing does not have the property that the minimum of the substitute function is the minimum of the global function. See, it just happens to work out for figure 7.7 for this one little substitute function. And when you add them all together, that doesn't hold anymore. So this picture is a little visually misleading because it suggests that the minimum of the substitute function is the global minimum of the true function. And that's true for just this one little function. But when you add them all together, it's no longer true.
Okay, but so you're you have a non-Gaussian, I guess, like your row function is non-Gaussian here, right? And then you do the ball bearing drop. You drop a quadratic into but if you're using a symmetric bound technique, then, I mean, your quadratic symmetric, your row function is symmetric. Why wouldn't they be minimal of the same?
Yeah. In fact, it's easy. In my mind, I know the answer to your question. I understand your question. It's an excellent one, and I know that the answer in my mind, but I don't know how to draw it visually without it being a huge confusing mess. But even if you added this, here, let's do it. Let me try to see if I can actually draw an example that illustrates what goes wrong. Okay, it's a really good question, and it shows that you're really thinking about the material, which is like delightful, honestly. Okay, let's say I take, let's say I have a function which is the L1 norm, so it's just like this, okay? And I add to that a quadratic function, so I'm minimizing something which is like, you know, the absolute value of x plus x minus x minus 3 squared, okay? Okay. Now what will happen is the overall function will look like something like, so the x minus 3 squared would be like, so it'll look like sort of like this. And it might be that the solution doesn't even fall at this thing here, okay? Now when I put this thing here, like that, okay, it's going to move, it's going to shift the minimum around.
Okay. So the confusion there is that your choice in the figure is, your choice of prior is symmetric, right? So, but there can be non-symmetric.
Right, and this would be like the data term.
Okay, yeah, all right,
So
okay.
the way to think about it is the prior is going to pull you in a certain direction. And actually what typically happens is that the substitute function is sort of more conservative than the actual. So it's not going to pull you as far as it should. But iterative application of it will eventually get you there.
Okay, that makes sense.
Okay.
So that's when so that some term, so if you're looking at, what would be equation 726? That was on the same page, it's just below your figure.
Okay, yeah.
So each individual, it seems, each individual row function, if you're going to finish, you can do it.
That's okay.
Okay.
Well, you're 20 seconds.
Okay, so each individual row function is symmetric, then that sum should be symmetric, but you're saying that the data term is in the forward row can pull it.
It's not
Okay,
symmetric. Yeah, absolutely. Yeah, you got it. Yeah, being a physicist, you think about symmetry a lot. It's a good thing to think about.
Okay, so we're basically out of time. Go and read this section again, because this is a really important idea, and when you understand this, you'll understand EM algorithm, which is a very important algorithm.
Okay. So
And then I know